In this video, we will be looking at section 4.6, which covers exponential and logarithmic models. A lot of times when we're talking about exponential and logarithmic models, we're going to be talking about half-life and doubling time. The half-life is the time it takes for half of a substance to decay, so how long it takes to cut in half. And doubling time is going to be the time that it takes for a quantity to double. So let's see if we can work with these ideas. You take 200 milligrams of a headache medicine, and after 4 hours, 120 milligrams remain in your system. If the effects of the medicine wear off when less than 80 milligrams remain, when will you need to take a second dose, assuming the amount of medicine in your system decays exponentially? So since we know that it's decaying exponentially, we are using an exponential equation, which generally we write in the form y equals ab to the x power, but since we're dealing with time, I'll use t. A means the amount that we're starting with. So we know that we're taking 200 to begin with, so we're going to be starting with y equals 200 b to the t power. But we know that after 4 hours, 120 milligrams remains. So 4 hours is going to be our time, t. 120 will be y, the amount remaining in the system. So we get 120 is equal to 200 times b raised to the 4th power. I can divide both sides by 200. And 120 divided by 200 is equal to 0.6. So we get 0.6 is equal to b to the 4th power. Let's zoom in a little bit. So if I want to solve for b, what I'm going to do is I'm going to raise both sides to the 1/4 power. So b is equal to 0.6 raised to the 1/4 power, and it looks like b is approximately equal to 0.8801. So now that we know what b is, we can plug that into our equation, and we get y is equal to 200 times b, which is 0.8801 raised to the t power. We want to know when we'll need to take a second dose, and the effects wear off when less than 80 milligrams remains. So what I'm going to do is I'm going to plug in 80 for how much remains, and we're going to solve for t, which is time. So we'll have 80 is equal to 200 times 0.8801 to the t. I'm going to divide both sides by 200, and 80 divided by 200 is 0.4. So we get 0.4, I'm going to do 0.4 because it makes me happy. 0.4 is equal to 0.8801 raised to the t power. I can take the log of both sides, so that the log of 0.4 is equal to the log of 0.8801 raised to the t power. Using Amanda's favorite log rule, also known as the exponent rule, we can take this exponent t and bring it out front, so that the log of 0.4 is equal to t times the log of 0.8801. To solve for t, I need to divide both sides by the log of 0.8801. Kind of ran out of room, so I'm going to go up here. So t is equal to the log of 0.4 divided by the log of 0.8801. And the log of 0.4 divided by the log of 0.8801 is approximately 7.17. Notice that earlier we were measuring time in hours, so that would mean that the effects are going to wear off after about 7.17 hours. that's what we're looking for. And the second one here, it says the half-life of fermium-253 is 3 days. If a sample initially contains 100 milligrams, how many milligrams will remain after 1 week? All right, well, we know we're working with the general form y equals ab to the t. So let's see what we can plug in. It says that we are initially starting with 100 milligrams. So that would be y equals 100b to the t. This time it's not clearly expressed, but we can figure out, based on this sentence, one of our points. The half-life is 3 days. So that means after 3 days, so time is going to be t equals 3, then the half-life, meaning we're going to be down to half of what we started with. If we started with 100, we're going to be down to 50. So 50 is equal to 100b cubed. I can divide both sides by 100, so 0.5 is equal to b cubed. And I'm going to raise both sides to the 1/3 power to solve for b. And b is equal to 0.5 to the 1/2 power, which is approximately equal to, oh, that should be the 1/3 power. 0.5 raised to the 1/3 power is about equal to 0.7937. So now that we have b, we can plug it in, and we will have y is equal to 100 times 0.7937 raised to the t. We're trying to figure out how many milligrams will remain after 1 week. And we were measuring t, which is time, in days before. So if we're looking at 1 week, that's going to be 7 days. So the amount remaining y is going to be equal to 100 times 0.7937 raised to the 7th power. So we get 100 times 0.7937 raised to the 7th power, which is approximately equal to 19.8424. And we were measuring the amount in milligrams. Next up, we're going to talk about Newton's law of cooling. And it says that the temperature of an object T in surrounding air with temperature T sub S will behave according to the formula T of T, yeah, lots of T's in this equation, is equal to A e to the kt plus T sub S, where lowercase t is time, A is a constant determined by the initial temperature of the object, and K is a constant, which is the continuous rate of cooling of the object. So let's see if we can use this Newton's law of cooling. A cup of coffee is 180 degrees when poured. The room the cup sits in is 76 degrees Fahrenheit. After 5 minutes, the temperature of the coffee is 168 degrees Fahrenheit. How long will it take the coffee to reach a temperature of 155 degrees Fahrenheit? I'm going to start by copying that formula over. That Newton's law of cooling says T of T is equal to A e to the kt plus T sub S. So let's see what information we're being given. T sub S is the temperature of the surrounding room. That one we have. They told us that is 76. So T sub S is 76. We know the temperature when the coffee is first poured. So the temperature at time 0 is equal to 180. And they also told us the temperature after 5 minutes. That's equal to 168. Let's see if we can work with that information to get us somewhere. So let's plug in what I can. If t sub s is equal to 76, then our formula so far is t of t equals ae to the kt plus 76. At least it's a start. Let's plug in t of 0 equals 180. That'll give us 180 is equal to a, whoops, that's not an a, e, we don't know k yet, but we do know t. T is 0 because we're plugging in 0 for t. And that is plus 76. If I subtract over the 76, then we get 104 is equal to a e to the 0, because k times 0 is going to be 0. But e to the 0 is just 1, so we get 104 is equal to a times 1, which is just a. So we now know a is equal to 104. So I'm going to update the formula I had before, because now we know a. So now we're working with t of t is equal to 104 e to the kt plus 76. We are a step closer. So now let's use the second piece of information. What happens after 5 minutes? We know t of 5 is equal to 168, so let's plug that in. So we get 168 is equal to 104 e to the k times 5 plus 76. All right, so let's start by subtracting the 76 over. If I do that, I get 92 is equal to 104 e to the 5k. I can divide both sides by 104. Oh, that's a gross decimal. That's 0.8846. Let's take it out a little bit further just to be safe. 15 is equal to e to the 5k. If I take the log of both sides, I'm dealing with e, so let's take the natural log of both sides. So the natural log of the left-hand side is equal to negative 0.122602. The natural log of this other side will be 5k times the natural log of e, but we know that the natural log of e is 1, so negative 0.122602 is equal to 5k. And if I divide by 5 on both sides, I'm getting that k is about equal to negative 0.02452. I know I'm not being super consistent about how many decimal places I go out, but in general, as long as you go out 4, you'll probably be okay. So now we have a k value, and I go back and update my formula one more time. And we have t of t is equal to 104 e to the k, which was negative 0.02452 times t plus 76. Now our goal is to figure out how long it will take for the cup of coffee to reach a temperature of 155. So 155 is going to be my final temperature. So it'll be 155 is equal to 104 e to the negative 0.02452 t plus 76. I can subtract the 76 over. So that 79 is equal to 104 e to the negative 0.02452 t. I can divide both sides by 104. And we get 0.759615 is equal to e to the negative 0.02452 t power. I need to get that exponent out of there, so I'm going to take the natural log of both sides. If I natural log the left-hand side, I'm coming up with negative 0.274943 is equal to The natural log of this is just going to be the negative 0.02452t. And if I divide both sides by that negative 0.02452, then I get t equals negative 0.274943 divided by the negative 0.02452. I still have this one. In my calculator, I'll divide it by negative 0.02452, which is approximately 11.2130. So it's going to take about 11.2 minutes, because that's what we were measuring time in, for this coffee to cool. So we've done a lot of talking about exponentials. We've used logarithms to help us solve a little bit. We're going to look at logarithmic scales for a minute. So we're going to take a look at some pretty big numbers. What I have here is a list of the planets and their average distance from the sun. So we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto will always be a planet to me. I don't care what the scientists say. Pluto is a planet. Okay, I actually do care what the scientists say, but in my heart, Pluto is a planet. If I try plotting this, I need to go from 58 up to almost 6,000. So this graph is going to be measuring distance in millions of miles. I need 6,000 at the very top. I need probably 0 at the lowest. That'll mean 3,000 falls in between. So halfway there will be 1,500, and halfway this way will be 4,500. Let's see if we can plot these. First, we'll do Mercury, which is at 58. That's like way down here. Mercury. Then we'll do Venus, which is at 108. It's going to be like right here. And it's probably even lower than that. Earth is 150, so we're still over here. Mars is at 228. Jupiter's at 779. It's going to be out there. Then we have Saturn, which is at 1430. We have Uranus at 2880. It's going to be about here. We have Neptune at 4,500. Hey, that one's going to be easy to graph. And finally, Pluto. Which is going to be pretty much right there. So you'll notice with the way we've graphed these that the first 1, 2, 3, 4, 5 are really packed together, and really the sixth one is pretty packed in there too. Whereas Uranus, Neptune, and Pluto are more spread out. This can be really hard to keep track of where everything is just because they're so close together in the beginning. And this is where logarithmic scales can come into play. Because we are dealing with such large numbers, what we can do instead is, instead of graphing them linearly, we can take the log of the distance and plot that instead. Because if we take the log of each of these numbers, look how different those are. I just need to go from about 1.76 to 3.77. And I'll just go from 0 to 4 just to be safe. If we put 0 here and 4 here, that'll put 2 in the middle. That's almost middle-ish. There we go. And 1 in the middle on this side, 3 in the middle on this side. If we now graph those planets again, you'll see that they're a lot more spread out and the graph will be easier to read. So Mercury is at 1.76. We have Venus at 2.03. We have Earth at 2.18. Mars at 2.36. We have Jupiter at 2.89. We have Saturn at 3.16. We have Uranus at 3.46. We have Neptune at 3.65. And finally Pluto at 3.77. That graph is a little bit easier to read because they're so spread out. Now I could have even started at 1 or even 1.5 down here and they'd be more spread out. Taking the log can make it a little bit easier to work with just because we can spread things out, especially with such large numbers. The last thing we're going to look at with logarithms and exponentials in this section is the moment magnitude scale. And the moment magnitude scale has a lot to do with earthquakes. So when you hear about like a 6.3 earthquake, we're going to learn about kind of what that means. So for an earthquake with seismic moment S, a measure of Earth movement, the MMS value or magnitude of the earthquake is given by M equals 2/3 times the log of S over S sub 0, where S sub 0 equals 10 to the 16th is a baseline measure for the seismic moment. I know these are a lot of words that may not quite make sense, but we'll work through using this equation so we can kind of compare two earthquakes. So if one earthquake has an MMS value of 6.2 and another has a magnitude of 7.7, how much more powerful in terms of Earth movement is the second earthquake? I'm going to go ahead and copy over that equation that we had. The magnitude is equal to 2/3 times the log of S over S sub 0. And S sub 0 is equal to 10 to the 16th power, which is a really, really big number. Now we have two different earthquakes that we're focusing on. Let's start with a 6.2, see what we can do with that. We know the magnitude is 6.2, so we'll replace the M in the equation with 6.2. That will be equal to 2/3 times the log of, since I have two earthquakes, I'm going to call this one S sub 1, and I'll call the other one S sub 2. And that's over the S sub 0, which we know is this 10 to the 16th. If I divide both sides by 2/3, or equivalently multiply by 3/2, 6.2 divided by 2/3 is 9.3. Is equal to the log of S sub 1 over S sub 0. I need to now put this in exponential form because I'm trying to figure out what this S1 is. So this is log base 10. So I'll have 10 to the 9.3 power is equal to S sub 1 over S sub 0. So if I multiply both sides by S sub 0, I get that S1 is equal to 10 raised to the 9.3 times S sub 0. I could multiply in what S sub 0 is, but I'm not going to for reasons of me knowing what's going to happen next. So let's deal with the second earthquake. It has a magnitude of 7.7. So we will have 7.7 is equal to 2/3 times the log of, I'm going to call this one S sub 2 over S sub 0. I'm going to divide both sides by 2/3 like I did last time. So 7.7 divided by 2/3 is 11.55. That's going to be equal to the log of S sub 2 over S sub 0. I'm going to put that in my exponential form. So 10 raised to the 11.55 power is equal to S sub 2 over S sub 0. And if I multiply both sides by S sub 0, I get S sub 2 is equal to 10 raised to the 11.55 power times S sub 0. So now what we have is how much the Earth is moving in the first earthquake and how much it's moving in the second earthquake. We want to know how many times bigger this one is than the first one. So what I'm going to do is I'm going to make a ratio out of these. S sub 2 over S sub 1, and that'll tell me how many times bigger the second earthquake was. That's equal to 10 raised to the 11.55 power times S sub 0 over 10 raised to the 9.3 power times S sub 0. The S sub 0's cancel out. And we get that the ratio is equal to 10 raised to the power of, since these both have the same base, I can subtract the exponents. And that leaves me with 2.25. And 10 raised to the 2.25 power is about 177.8279. So that second earthquake with a magnitude of 7.7 is about 178 times more powerful. That's a lot. So when you hear about earthquakes in the future, think of them as really, we're working with logs, so these numbers are a lot bigger than you think. So the difference between a 6.2 magnitude and a 7.7 is very large.